So we're facing a challenge from the business perspective. The intrinsic randomness of the different learning machine models that are being used that makes them dependent on the random seeds, hence on the initial conditions, makes everything slower. Training gets much more difficult and increases costs. Moreover, the lack of certainty that the result is the best one adds operational risks for our customers because we cannot offer them a sure result, a result that we can guarantee is the best. And it makes it difficult for Anastasia to differentiate from the competition because if, for example, we perform a demonstration for a customer and we get some results, it may have been sheer luck that we got those results, and it could have been bad luck. And then comes somebody from the competition, but also by sheer luck gets better results. So that's why we developed our own recursive neural network, which is mathematically characterized to absorb these problems. There you see plots showing how our system is able to absorb initial conditions and behave in a very robust way. What are the implications of this? That when we run it in SigOpt, this is again captured from SigOpt's interface, the system quickly converges to the desired solution. There is a difference of scale compared to the previous plot, so that's not fair. But the important thing here is that in less than close to, I would say, 25 observations, we are right on the result. So having a system, a learning machine model that's able to absorb initial conditions allows us to perform at least one order of magnitude less to do the hyperparameter search with at least one order of magnitude less of resources, which is very important because that translates immediately in faster and cheaper results for our customers. Moreover, in terms of the importance, the relevance of the parameters, we see that in this case, SigOpt is not tricked by the fuzziness of the results. I quickly discovered that the delay, which is the amount of data we have to look for in the past in order to produce an accurate forecast, is the most important variable. So when you eliminate the intrinsic randomness of the model, SigOpt can work much faster, and we can focus quickly our machines into finding the correct hyperparameters precisely. Even more, when we run 100 different random seeds and we produce 100 different forecasts, we get exactly the same prediction all the time, which is the best prediction, which is the one you're seeing also in the green line there. But in contrast to XGBoost, here the error is 7.93, where in XGBoost the average, the mean was 8.2 something. So it is an improvement, but also we can guarantee that this is the best solution because the XRNN, as we call it, is totally mathematically characterized. So we know that we're getting the best result. And thanks to that, we have a much simpler training pipeline backed up with an efficient hyperparameter optimization, which ensures that we're focusing on the right parameters. And better, we can scale this up into very complex architectures, ensuring this behavior in all levels.